All right, so this is where we left off yesterday, and this is what's so cool about it, is that we have our situation, we use the computer to measure the speeds. We had a 0.5 kilogram car coming in hot at 0.6 meters per second, hitting and sticking to a 1 kilogram cart, and then the two move off together at 0.2 meters per second. Is that cool? We can calculate the kinetic energy before, calculate the kinetic energy after. It's a little bit less because you lost some of the thermal. We've done that a bunch of times, no big whoop. But now I want to use this chart here to calculate what we call the motion quantity. Now, as I mentioned before, this motion quantity can be calculated by taking the mass times the velocity. So this part is the mass, this part here is the velocity, and then the area is the motion quantity. Is that all right? So, yeah?
I just had a question, not about the motion quantity, but like about the situation if the two cars are repelling, the like magnetic energy field thing? You know?
Yes. So if this is one of those where it comes in and they don't actually physically collide, but this one pushes this one through the magnetic field, as it comes in, energy is stored in the magnetic field and then released out of the magnetic field. So that's exactly what happens. But because cart A and cart B are both inside the system, we could actually include the magnetic field inside the system also, which would mean you're transferring kinetic energy from A into the field and then from the field into B. So that would be a much more robust understanding of that. So yeah, 100%. Okay? All right, so get ready because this is the cool part. So what do I have over here on the left? Do I have two objects? I do, right? What's the mass of the green one? It's a half kilogram, right? So I'm going to draw it here, right on the axis, half kilogram. All right, you see that? All right, and what about the blue one? How much?
1 kilogram.
It's 1 kilogram. So how much longer am I going to draw it on the mass axis? Twice as long. You see how that works? All right, so this is 1 kilogram long here. And this one is 0.5 kilograms. Now, is the blue one moving? So we don't draw any velocity left or right. Is the green one moving? Yes, it is. How fast? 0.6. So I'm going to draw it 0.6 long. Now, it doesn't actually matter how long it is. It just matters the fact that if we're going to draw this one 0.6, anything else relative to that should be the same length. So if there's another 0.6 meters per second on here, I would draw the same length. If there's a 0.3 meters per second on here, I would draw it half as big. Cool? Okay, so now let's see what's happening over here. I still have my same masses, so here's my half kilogram. Here's my full kilogram. Again, twice as big. And what do we know? Now they're moving at 0.2 meters per second. But they're attached, so this one is also moving at 0.2. All right, how's that look? So now let's calculate the area of each. Okay, now let's calculate the area of each and see what we notice. Yeah?
Since they're almost one object now, would we still have to separate them into 0.5 and the 1, or could we just do 1.5?
You could just do 1. So he said, look, I'm just going to draw 1 over here. I'm going to make it a new color. I'm going to draw 1 here with this size. That totally works. That totally works. So let's look at this. What is the area of this right here? Well, it's 0.5 times 0.6. What's 0.5 times 0.6? Half of 0.6 is?
0.3.
So the motion quantity before the collision is 0.3. Is that cool? What's the total area afterward? Well, my total height is 1.5. 1.5 times 0.2 is how much? It's 0.3 again. What ends up happening here is you have it, it's not very tall, but it's very wide. When it hits the other one, it becomes very tall, but now what do you notice? Now it's not very wide. How do you think the area before compares with the area after? Check with your neighbor right now. How does the area before compare with the area after? See what your neighbor says. Do you notice that it's the same? And so what we're going to find out here is that the motion quantity before has to be equal to the total motion quantity after. So when you draw these, you should notice that the area before equals the area after. That is what we're going to see if that holds true for your boards today. Is that cool? So you're going to cruise back to your stations now. Keep your energy diagrams, but erase whatever numbers or stuff you have on here. Draw these motion quantity diagrams on there. Do them with fidelity so that your sizes all match up in a way that's meaningful, and then we'll compare them. All right? Ready, set, go!
How did my fingers here?
Well, we'll just have to do it together, me and you.